we can write the displacements inside the element using this isoparametric form. So if you remember, that involved the shape functions and the nodal values. Okay, so we had U. So we had U is equal to N1 Q1 plus N2 Q3. Ooh, what did I do there? Let me show you. And I write this one Q5. Okay, so if you remember, our element here is 1, 2, 3. Our degrees of freedom are, we had a Q1, if you remember, our local displacement vector, Q1, then we had Q2. So for one node, node 1, it has 2 degrees of freedom associated with it, right? And we name those sequentially, 1 and 2. Our next one, node 2, what was that? That was Q, well, we already have 2, so we need Q3. And this is going to be, the Y will be Q4. So you can see that that's why over here we have a 1 and a 3, because it's shape function 1 associated with Q1, that's the x direction, degree of freedom, local displacement value. And 2 is associated with node 2, and Q3 is the x value associated with U for node 2. Okay, so likewise, you can guess that N3, we're going to have Q5, and because I wrote this a little bit backwards here, and Q6. Okay. All right, so that's kind of why it's written like that. Can you guess what the Y displacement is going to be? V is equal to N1 times Q2, right? The Y component of that local displacement, plus Q2 plus N2 Q4 plus N3 Q6. Okay. We know the shape functions. We know what the values are for N1, N2, N3 in terms of psi and eta, right? We wrote those. So we can substitute that in. So we could do U is equal to, now you can rearrange this also, because remember, N1 is equal to psi, N2 is equal to eta, N3 is equal to 1 minus psi minus eta. And so we're going to have this term, which is Q1 minus Q5 with both with a term of eta, right? So we can simplify that. Q5 after rearranging plus Q3 minus Q5 eta plus Q5. V similarly is going to be equal to Q2 minus Q6 psi plus Q4 minus Q6 eta plus Q6. And then what we can actually do is simplify. Remember the term that we really want to get for this fine element program, if we were to write it like in what we did in 1D, remember we had in 1D, we had U is equal to NQ, right? So that's what we had in 1D. If we want to do that here, what we need to do is pull our shape functions out. So make a matrix or vector with all the psi and eta values, such a way, rearranged in a way, that when it multiplies by the Q vector, the Q1 through Q6, it gives us these values back, right? So if you play that trick with linear algebra, you can actually write an N matrix that gives you that. And that is it looks like this. So this can be written in matrix form by defining a shape function matrix All right, and that's going to look like n. So it's actually a matrix, it's not a vector in this case. It's equal to n1, 0, n2, 0, n3, 0, 0, n1, 0, n2, 0, n3. It kind of alternates. But you can see that we filled it in with zeros, and when you multiply it times q vector, 1 through q1 through q6, you can actually write this. So this is actually a matrix, and you actually get this equation back. All right, so pretty interesting when we're writing displacements in terms of shape functions. Now, if you remember what it means to be isoparametric, it means that you can write that for the x locations also. So in that case, we have x is equal to n1 x1 plus n2 x2 plus n3 x3. Y is equal to n1 y1 n2 y2 plus n3 y3. Or we can write x is equal to x1 minus x3 if we make the substitution now with what those n values represent, plus x2 minus x3 eta plus x3. Y is going to be equal to y1 minus y3 plus y2 minus y3 plus y3. Okay, now what we can do is use the notations where the subscript ij represents the subtraction there. Okay, so if we have x is equal to x13, okay, and that represents this term right here, okay, x13 eta plus x23 eta, sorry, that was psi, x13 psi plus x23 eta plus x3, and y is equal to y13 psi plus y23 eta plus y3. Okay, we've written like a shorthand version of this. This is typically the place where students say, why are we doing this? Why do we have to represent with all these crazy natural coordinates? And the reason, one of the best reasons I have for this, one of the best reasons I have for this is that it allows us to implement it a lot easier. That's one very practical reason, is that it standardizes the form of the finite element implementation. If we put in isoparametric coordinates, that is, we have a master element, we have shape functions, we have derivatives of shape functions, we have ways to represent different points within the element using interpolation. So I think the biggest reason, there might be others, but the biggest reason is really implementation, ease of implementation. And that's something that we haven't really got into, so it might be hard to understand. But all modern finite element codes are using this isoparametric form. So, you know, it's really a good thing to learn, and it does make our life easier as we go forward and get, you know, soon we're going to get in a little bit more of the implementation details, and it does help with those things. Okay, so that goes over how to use isoparametric formulation in the constant strain triangle. We can probably look at a simple example of this and demonstrate it. We also need to continue our discussion of how do we extend this further into the finite element procedures. We haven't got into things like the derivatives of the shape functions, the B matrix, strains and so forth. So we're going to do that in the upcoming lectures. We'll save that for next time. I'll see you then.